This is application security. This is how you engineer secure software and how you can get prepared for the Security Plus exam. First off, the ubiquity of code and the need for structural logic. Software is everywhere in our organizations, ranging from customer-facing applications to the smallest custom scripts supporting business needs. Creating and maintaining this ecosystem requires more than coding skills. The solution? The Software Development Lifecycle, or SDLC. This is the consistent framework used to structure workflow and provide planning. Simply picking an SDLC model isn't enough. You have to choose the right model that fits the work in a You have to choose a model that fits the work. Governance. So on the exam, Domain 5 highlights the policies that are specifically regarding SDLC that are a core element of effective security governance. Security isn't simply a technical task, it is a policy mandate, i.e., in order to have security, you can't just have someone technical just go in there and fix everything up. You have to do it from start to finish in your policy to be secure. So the anatomy of the SDLC. We start off with planning. We check out the feasibility and costs. Next we have the requirements, where we check out the functionality and the security needs. We have the data flows and integration in the design section. Then we have coding in the construction and unit tests. In testing, we have quality assurance and user acceptance. In training and transition, we have deployment and install. And in operations and maintenance, we have the ongoing patching and daily support. And then in decommissioning, we have disposal and data preservation. Now, while the phase order may vary, that is linear versus iterative, successful life cycles contain forms of each phase. Now, the foundation layers that are phases 1 through 3, planning through design. So you can see planning through the design. So first off, phase 1 planning. This is where you would figure out whether you want to do this effort or not. You look at the alternatives and you look at the costs from a high level. You don't get into the too nitty-gritty details with the budget. Next up is the requirements. You need to figure out, what do I want out of this? What do I need out of this? And this phase must design the security needs as well. So that is, you can define your secure coding practices at this stage. And then moving on to design, you will design for functionality, architecture, business process, and specifically mapping data flows and integration points. Then we have construction and verification. So phase 4 coding is where you actually write the application, and you're going to want to be writing unit tests during this, which is where you test small components individually to ensure they function properly. And this is usually performed by the developers. Whereas with QA, they would do formal testing outside of the development team. So they would verify the functionality and the connections function as wanted, as desired. And they would also have UAT, which is user acceptance training, which is where you ensure end users are satisfied with the functionality. And then phase 6, after the software enters general use, that is after acceptance, installation, and deployment, you would ensure you securely hand over comprehensive documentation for these day-to-day operations, so that while they install it, if there's any hiccups, they know how to deal with it. Now, phases 7 and 8, you would live with this application. So this is usually the longest phase. This goes on as long as from when the application is deployed to when it's retired. So that would include patching, updating, minor modifications, and daily support work. And phase 8 is decommissioning, which is when the system reaches the end of life. So often they don't decommission stuff in the excitement of new products, or let me correct that. They decommission stuff because in the wake of new products, people don't care about the old ones anymore. So they're going to shut down the old products because no one cares about it. They ignore it now. So they shut it down to save costs. But something that's critical to this is that the data and the systems must be preserved or properly disposed of. So you're going to want to ensure secure and compliant data archiving, secure deletion of sensitive information, and a proper disposal of the hardware. Now, the engine of this is DevOps to DevSecOps. So DevOps is just software development and IT operations to optimize SDLC using tool chains, that is, tools for coding, building, testing, packaging, and releasing. Whereas DevSecOps is where you integrate security into DevOps, so that you understand better that security is a shared responsibility and you have to keep it in mind throughout the entire cycle, not just something you do at the end. And you're going to have threat analysis, planning, testing, and feedback throughout the loop of development. Now, the assembly line is CI/CD. So these are two schools of thought. So CI is continuous integration, which is a development practice where code is consistently checked into a shared repository. Frequent check-ins trigger automated builds and testing. The goal of this is early detection of any sort of security vulnerabilities, because you can easily look at the code that's there and audit it and deploy it if you would like to. Then we have CD, which is continuous deployment, which is paired with CI to roll out tested changes to production automatically as soon as they pass tests. So that is, after you CI it, after you put all your stuff into a shared repo, you can then deploy it all at once. That way you can do it as quick as possible. But the problem with the speed is that it creates a risk. So without automated security testing, validation, new vulnerabilities can also be deployed instantly. So for example, a rogue developer, which is an untrusted developer, they could insert flaws and remove them in the next cycle before detection, so that it would be deployed and no one would be the wiser. So just visualizing this pipeline, a developer would commit a change, the build process would be triggered, the build report would be delivered, the test would be run against the build, the test report would be delivered, and if both of those are successful, the code is deployed. So to secure this pipeline, you're going to want to integrate scanning, updates, and config management tools directly into all these steps. Now, the ecosystem of development environments includes development, test, staging, and production. Development is where they build it. That's the environment where the developers can build, do their work. They can either be individual or shared, usually it's a mix of both. Then we have test, which is the quality assurance, where they prove the software so they can test it without impacting the production. So this is pre-production. Next up is staging, where the code has cleared the testing, and ideally they would be able to just mirror it straight over to there and deploy it. So what this means is during QA, they're working on an offline cold and air gap system to test, and then when they determine it's good enough, they'll just mirror it onto the deployment environment, the production environment, exactly as it is, if it passes all the tests, or they change stuff and then they mirror it. And lastly is the production environment, which is the live system, where only tested and approved changes can enter. So controlling this flow is done with change management. So the governed process is where you move code between the environments, dev, test, stage, and prod, without just copying it. You have to govern it. So you'll have a gatekeeper, which changes the gatekeeper includes change management processes to ensure accountability, oversight, and gatekeepers are required for auditing and compliance. So the SDLC maps software creation from idea to rollout. Secure SDLC practices aim to integrate security into the development process itself. That is at every step of the way. So to design for the security, you have to shift left. So you're going to want to shift left from testing back and look back at the requirements. So you're going to have early intervention. That is, the first chance to help is in requirements and design. So you have to plan for how you're going to secure your app in the very beginning, not at the very end. You're going to want to use secure test coding techniques and code reviews during development. And when you're testing it, you're going to want to test fully integrated software using both web app security scanners, penetration testing techniques, and more. And this establishes a baseline for future regressive testing. So the SHIELD, which is OWASP proactive controls. This is input and access standards. So you're going to want to validate all your inputs, you want to treat as untrusted implicitly and then validate it. You're going to want to have encode and escape data. So you're going to want to get rid of special characters to prevent these injection attacks. You're going to want to implement digital identity by using MFA, multi-factor authentication, secure password storage and recovery, and secure session handling. And you're going to want to enforce access controls. So you're going to want to require all requests to go through the access controls. You want to deny by default and apply the principle of least privilege. So the second part of that is in data protection operations. You're going to want to protect data everywhere. That is encryption in transit and at rest. You're going to want to have secure database access. You want to pre-build SQL queries to prevent injection. And you're going to want to configure databases for secure access. In security logging and monitoring, you will enable these to enable detection and investigation. And logging must be designed to fix the CI/CD process. And finally, you're going to want to handle errors and exceptions properly. You're going to want to fail gracefully. Applications must not leak sensitive data in error messages. Now, the interface risk is in API security. APIs define how clients ask for information and how servers respond. The risk arises because APIs are tremendously useful, but they represent a significant point of vulnerability if they're not secured. Domains 2.3 and 2.4 cover application attacks, injection, and indicators of malicious activity. Governance, the rule of law. So in secure software, these are upheld by 3 pillars: policy, process, and practice. In policy, you're going to want to define the SDLC and standards, and this is reviewed in Domain 5.0, Security Program Management. Next, you're going to want to, in the process, you're going to want to adhere to change management and automation. And the benefits of automation are efficiency, enforcing baselines, and reaction time. Then finally, in practice, you're going to want to utilize OWASP standards and DevSecOps. Now remember, security is an ongoing cycle of improvement, not a destination. Now let's go to software security, testing methodologies and vulnerabilities, from static analysis to advanced attacks. The imperative for rigorous testing. Vericode's 2023 metrics showed that 74% of applications scanned exhibited at least one security issue during the testing process. Now, what's the core message is? No matter how talented the development team, flaws are inevitable. This necessitates integrating software security testing deeply into the software development lifecycle, or SDLC. Now, what are some approaches to analyzing and testing code? We have both static and dynamic. Static is where you review the source code itself. That is, you just read the code. Whereas dynamic is where you execute the code with a respective input. So you can see how the code security holds up when it's being ran. So the goal of both of these is to identify bugs, syntax errors, business logic flaws, and integration issues. And regression testing includes once changes are made, the code must be retested to ensure no new security issues were created. Now, in situ, you're going to want to do both of these analyses. You're going to want to read the code itself, look if you have any linting errors and whatnot. But you're also going to do dynamic analysis by running the code with some input, so you can also see how's the security hold up while it's being run with input. So let's circle back to static code analysis, or white box testing. So static code analysis is a method conducted by reviewing the source code without running the program. It focuses on understanding how the program is written and what it's intended to do. Now, the key characteristics of this are full visibility, which is a known environment testing where testers see everything, and detection. It is excellent for finding known issues and programmer-induced errors. So just keep this in mind, okay? Static testing analyzes code without execution. It points developers directly to vulnerabilities and often provides specific remediation suggestions. That is, like if you have one line and it's really hurting your security, you can easily just go in and change that one line because you know it specifically originates from that one line. Now with dynamic or black box testing, you will rely on the execution of the code while providing it input to test the software. So this simulates a user interacting with the application interfaces, and it's usually automated due to the volume of tests required. So unlike static analysis, which points to a line of code, dynamic analysis points to a vulnerable feature. So as an exam note, dynamic testing runs all interfaces exposed to the user with a variety of inputs, searching for vulnerabilities during runtime. Now what's fuzzing? Fuzzing is when you send invalid, random, or unexpected data to an application to test its ability to handle exceptions. So this is strong for detecting input validation issues, memory leaks, error handling flaws, but it's weak for complex logic or business process issues, and it may not provide complete code coverage. Now, with API security, you're going to want to secure your interface, and security professionals are often asked to write scripts to pull data via APIs, which is why API security is paramount and so prudent. So how can you implement API security? You can do this through authentication authorization, rate limiting, input filtering, and monitoring and logging. And OAuth's API security provides a standard breakdown of these techniques. Now the threat landscape includes injection vulnerabilities, which is a class of vulnerabilities where an attacker supplies some type of code to the web application as input, tricking the web server into executing that code or passing it onto another server. Now the risk with this is that these are among the primary mechanisms attackers use to break through web applications and gain access to supporting systems. Now what is the anatomy of a standard SQL query? So a user searches for an orange tiger pillow on an e-commerce site. So because this commerce site is using SQL for search, their code would look like this. They're looking at the table called products, and for the parameters they have item name, description, and price. And they're putting in each keyword separately, and this is how most search engines do this. They put in each keyword separately. So what do you guys think that this would show you? Actually, it's not separately because they have these and things at the end. So it has to be, all three of those have to be true. So even though Google and most of them do each one separately or more intelligently, obviously it's a very rudimentary search. Anyway, so this would give you the exact result of something that includes orange, tiger, and pillow. So to execute this injection, they would put a crafted string into the search box, and because they're not cleansing their search properly, all that code would just get executed like this. So what does the malicious code exactly do? So you can see it closes the data field, ends the first command, injects new command for sensitive data, and comments out the remainder of the original query. So the mechanics of stack queries. So this is an attack vector where the perpetrator creates a second distinct SQL query separated by a semicolon. Now this attack is constrained by the web application's capability of returning multiple result sets. If it can't return multiple, then it won't be visible if you use this. Now, what is a blind SQL injection? Well, many web apps do not provide the attacker with a means to directly view the results of an attack. They don't have error messages and they don't have data dumps. So the solution is, even without seeing the data, you can still do this attack. Attackers would use blind SQL injection to infer data by asking the database true and false questions. These can be two types, content-based or timing-based. So they could put in something that would change the page's content, or they could put in a delay thing to change how fast the page loads. So what's a content-based blind injection? So they could put in some code wherein, even though it won't show the output, they'll put in code wherein if their thing is false, then the page won't load. So you can see with these screenshots, it was able to find Mike's account number because they changed the thing that's always true and they turn it into something wherein they both need to be true. And since one of them's false, then if the other one's false, then it'll be false. So again, if the application returns a blank page for the false test, but a normal page for the true test, then it is vulnerable. Now, what is a timing-based blind injection? This is where you use the database's processing time as a communication channel. So if the web page hangs for exactly 15 seconds before loading, the application is vulnerable, and the attacker now knows that their code is executing. Now, how do you extract data through time? An attacker can discover a password letter by letter by asking, is the first letter A? If yes, wait 15 seconds. Now, while this is tedious, manually, tools like SQLmap and Metasploit can automate this process, making data extraction straightforward and fast. Now, beyond the database, we have code and command injection. So code injection is a broad category that includes SQL injection, which we just went over, and command injection, which is targeting an operating system. This is a mechanism to exploit a flaw and execute shell commands directly on the server. And the danger of this is that it allows direct manipulation of the OS, often leading to full server compromise. Now, what is the injection attacks family tree? This includes LDAP injection, DLL injection, XML injection, and cross-site scripting. And the key takeaways of this are you're going to want to test early and often. You're going to want to use static analysis for code understanding and dynamic analysis to test runtime behavior. You're going to want to verify your inputs. So, for example, fuzzing can help identify how your apps handle invalid data. You're going to want to look at the injection rule, so any environment that inserts user-supplied input into code is vulnerable. So you're going to want to defend it by sanitizing all your inputs. So if the attacker can inject a quote or a semicolon, then they can easily alter the logic of your operation. Now, as a note, in a SQL injection attack, malicious code is inserted into strings of code that are later passed to a SQL database server. Now let's deconstruct web vulnerabilities from an attacker's perspective. Do you guys remember? Think like an adversary, alright? So the modern web attack surface includes authentication, session management, authorization, and input validation. The weakest link is password authentication because passwords are a knowledge-based mechanism. If an attacker learns the secret, they'll become the user until the password is changed. Now, social engineering is where you trick the users into revealing secrets directly or through false forms. Eavesdropping is intercepting credentials over unencrypted network traffic. And password dumps are exploiting reuse, where the attackers obtain dumps from compromised sites. And these three are ways that you could get passwords. Now, another hazard with passwords is the default danger. So if you leave the default administrative accounts unchanged, that is, you leave it with the default password, then they can easily hack in using the public documentation that's in the user manual or otherwise. So if you just leave your password as admin1234, then they can easily get in. Now we have to understand sessions and statelessness. HTTP is stateless. To avoid re-authentication for each page load, applications use cookies. A cookie is a small database in the browser containing an authentication string. So you can see kind of a flow chart of how cookies work. Now cookies are like conference badges. You show it once and you get a badge. They check the badge, not the ID. That is, they don't ask you for your password every single time you go to a website. They're just going to ask to see your conference badge or your cookie. And the problem is, if someone steals your badge, they have your access because they're not looking at your ID or your face, i.e. they're not looking at your password, just your badge, i.e. cookie. And then we have credential stealing versus session hijacking. So credential stealing requires cracking or finding the login information, whereas session hijacking bypasses the authentication mechanism entirely. The attacker can take over an already authenticated session. Now, how do attackers obtain the active cookie? They can get it through, again, eavesdropping, malware, or on-path attacks. On-path is kind of like phishing. Now, what is a session replay attack? It's where you can, once the attacker gets the cookie, they can use it, they can emulate you, and they can gain access to your session. Now, a note is, the secure cookie attribute ensures cookies are never transmitted overall over unencrypted HTTP connections, only HTTPS, and this will rule out these eavesdropping attacks. Now again, authentication is not authorization. Authentication means when they're first checking, who are you? And then authorization is, what are you allowed to do? So the exploit is, even if a user is valid, the application may fail to check if they are authorized to view specific data, and this would break the C in the CIA triad. So an IDOR, or an insecure direct object reference, is where a system retrieves the document based solely on the argument provided in the query string without checking if the current user owns that document. That is, like, if they have the permission to view it. Instead, it will just serve it to them because they have the ID for it. So a case study for this is the Nova Scotia breach. So in April 2018, a 19-year-old was charged with unauthorized use of a computer. He noticed URLs on the Freedom of Information portal contained sequential integers. He wrote a script to increment the ID, downloading over 7,000 documents. And a quote is, cyber professionals noted this wasn't a sophisticated attack, but a failure of the province to implement basic authorization checks. And of course, more recently, the Epstein files had the same issue where if the DOJ restricted access, they de-indexed a certain document. So that is, you couldn't just click a link on the DOJ website to see it. You could still just type in the same ID and get back to the same document. So this is the same attack. They tried getting rid of your access to it, but you could just change the ID of the website URL and get access to it again. Now, directory traversal is where the attacker uses ... to move up the directory structure from the web root to access sensitive files outside the intended web server boundaries. And then we have unvalidated redirects, which is a mechanism where you modify a redirect URL to phish users. So if they only see the first part of the URL, then they're not going to see the part where it says redirect, and it takes you to the bad location. And the defense for this is by whitelisting your allowed location, that is only allowing specific ones and everyone else is blacklisted. Now, command injection is when input becomes instruction. So if an application takes user input and passes it directly to the underlying operating system without sanitization, then the input ceases to be passive data and becomes an executable command. So the setup for this is, if you have the account creation page and this links directly into your OS as a command, then you can see that when someone types in that, it'll make a new folder. That's the intended behavior. But someone can take advantage of that and run another command using and. So not only does it create this directory, you see the make dir is already there, but on top of that, it'll also delete the entire thing. Now, how do you defend against this? You're going to want to use secure cookie attributes and HTTPS to prevent theft. You're going to want to validate permissions for every object request, not just the user identity. You're going to want to implement strict whitelisting of allowed destination URLs. And you're going to want to sanitize your inputs so to never pass user input directly to the system. You're going to want to validate and sanitize it. Security is anticipating unintended use. The developers of the Zixel router, the Nova Scotia portal, and the student account system build features that worked for the intended user. Vulnerabilities exist where developers assume input will follow the rules, but secure design requires assuming the input is hostile. Think like an adversary. You're going to want to deconstruct and prepare based on the analysis of common web application vulnerabilities, so IDOR, injection, session hijacking. Next up, we have exploiting and securing web applications. The attack surface. Complexity is vulnerability. Web applications aren't just one thing. They're complex ecosystems, and this complexity creates a fertile ground for pen testers and attackers, where you might oversee something, but they definitely won't, and they will take advantage to it to the fullest. That's why defenders must secure the entire chain, because a flaw in any single component opens a door to exploits. So client-side attacks, reflected cross-site scripting. Cross-site scripting is fundamentally HTML injection. It occurs when an application allows the user to insert their own HTML code into a web page, which the browser then executes because it trusts the source. So you can see with this code, the browser is executing the script instead of just displaying the name. Now, what is worse than reflected is persistent, where you embed a secret hidden script in, say, a message board where user input is stored on a database. Then they store it to the database, and whoever views it will execute that script. And this happened with the Twitter thing, where they had a bunch of cross-site scripting and a bunch of people were forced to retweet something. And that wasn't particularly malicious, but it definitely taught Twitter a lesson. I think this was in 2013. Then we have trust exploitation, cross-site request forgery. So CSRF exploits the server's trust in the user's browser. If a user is logged into a sensitive service like banking, an attacker can trick their browser into sending a command without the user's knowledge. And note that this attack occurs without direct user interaction with the legitimate site. So you can see they're forging a request cross-site. Now we have server-side request forgery, which is where the attacker breaks into the server and forces the server to fetch a URL. Now because the request comes from the server itself, it won't have any external firewalls and restrictions, and it'll be able to access these internal dashboards or cloud metadata. And then we have directory traversals, where people use the // operator to navigate out of the web directory and access restricted OS files like password hashes. That's by getting into /etc/shadow. So file inclusion is a way that direct access occurs. So local file inclusion is where you execute a file already hidden on the server. So you get the file onto the server and then you can remotely execute it. Now remote file inclusion is where you force the server to fetch and run external code. So you're forcing the thing to get this malicious code from somewhere else first and then run it. Now this allows attackers to execute arbitrary commands using standard HTTP traffic, often evading detection. Now another logic bypass is parameter pollution, which is where you confuse a filter. By sending multiple values for the same variable, attackers can trick security filters that only check the first value, while the application processes the second malicious value. So then privilege escalation. a case study for this is Dirty Cow, which is a Linux kernel vulnerability in October 2016. It existed for 9 years before it was discovered. It was extremely easy to exploit, and it allowed normal users to gain root-level administrative control. And the goal of this was to transform a restricted user into a super user. The primary defense against this is input validation. And the golden rule is to never trust user input. You want to take the user input and you want to filter it for server processing. You don't want to do client-side validation though, because that occurs in the browser and it's only for the UX, and it's very easily bypassed by the attackers. Instead, you're going to want to do server-side validation, which occurs on the server, and the only effective way to stop XSS, SQL injection, and other injections. Now, another defense strategy is allow listing, which is the gold standard of whitelisting, where you define exactly what is allowed and everything else gets rejected. And this is the most effective form of input validation because it is precise and leaves no room for unexpected malicious syntax. Another defense strategy is deny listing, or known as blacklisting. But this is worse because it only defines what is bad and blocks that, and it is very difficult to list every single possible malicious string. Let's say you block single quotes to stop it. Then someone inputs O'Brien, which is a name, and it gets blocked because it's a false positive. Deny listing often breaks valid functionality or fails when attackers find a syntax you forgot to block. That is parameter pollution. As a summary to build robust defenses, the threats include injection, cross-site scripting, trust, CSRF and SSRF, direct access, traversal and file inclusion, and logic, parameter pollution, and privilege escalation. And the defense against these: secure coding, server-side input validation, strategy, allow listing, and infrastructure security tools to detect blocking exploits. Because security is not a product, but it's a process of validation and architectural vigilance. Now we're going to talk about the different phases. Again, you're going to want to avoid a single point of failure. You're going to maintain a diverse software. So just as financial portfolios require you to diversify, software environments must also avoid reliance on single components to maintain availability. Security professionals must identify dependencies on single pieces of source code, binary executable files, or compilers. While eliminating all dependencies is impossible, tracking them is critical. So if an issue arises within a single ubiquitous component, the entire environment is at risk. So the dual nature of source code comments. Now, while comments are crucial for documentation, explaining design choices, and helping teammates troubleshoot complex logic, when they're exposed, comments serve as a roadmap. They may reveal how code works and may accidentally include critical security details that should remain secret. Now, what do you want to do? You want to strip all your comments from the production versions. Do not leave internal logic accessible to unknown individuals on the internet. Now, the vulnerability of hard-coded credentials. Now, some developers may put in a maintenance account that is hard-coded to regain access if the authentication protocol fails. If this backdoor is discovered, all production copies are compromised. Another variation of this is service credentials, which is where you include API keys or access credentials for third-party services directly in the source code. So for instance, if you leave like your OpenAI API key and I just grab it and I run up like a humongous bill, you're gonna have to pay it. Now, the risk with GitHub is that these credentials often leak when developers accidentally publish code to public repositories, and once it's public, the keys are compromised immediately because they are being stored in the code. This is why you want to have a git ignore. Now, the anatomy of a leak when your errors say too much. So, the French website SQL error. You don't need to understand French to understand the exploit path here. The error message explicitly details the SQL syntax error, allowing an attacker to map the database structure and craft a precise SQL injection attack. The golden rule of this is overly verbose error handling routines present a risk. Never display internal logic or system details to the end user. Keep it generic and keep it high brevity. Handling the unexpected, resilience and defense in depth. Attackers like to test boundaries. For example, entering a 50,000 digit integer into an H field to test an integer overflow. Now, the strategy in defense in depth is, first off, you're going to want to have input validations. You're going to want to attempt to stop the malformed data before it gets processed. But if validation fails, error handling serves as a second control to prevent the application from crashing or triggering a dangerous condition. You're going to want to fail gracefully. It's like two safety nets. So to manage resource and prevent exhaustion, applications must manage their own memory usage. Poor practices here undermine the security of the entire system. Now, the threat is a resource exhaustion, whether intentional attack or accidental bug. Consuming all available memory, storage, or processing time disables the system for other users. Memory leaks occur when an application requests memory from the OS but fails to release it. Over time, this cripples availability. The assembly hub, code repositories. Code repositories give you three things. Version control, which allows you to track the changes and roll back to previous secure states if you introduce a vulnerability. Auditing, which is where automated logging creates an unalterable record of who changed what and when. And housekeeping, you prevent dead code, code that is running but no longer maintained or tracked, where vulnerabilities can hide unnoticed. The risks of code reuse and SDKs. Developers rely on third-party libraries and software development kits to save time. SDKs provide documentation, examples, and specialized utilities. But when you import a library, you import its vulnerabilities. It's common for security flaws to arise in shared code objects that perform related functions. For example, financial analysis or social media integration. So as a requirement, security teams must ensure outsourced or third-party code is subjected to the same level of rigorous testing as internally developed code. You don't want to be importing vulnerabilities. Now, validating the supply chain, you can do this through two techniques. Package monitoring, which is where you keep track of all your third-party libraries. You're going to want to use automated tools to identify outdated dependencies and only use packages from trusted repositories. And the second technique is integrity measurement, which is ensuring code hasn't changed between approval and release using cryptographic hash functions. Any deviation in hash values indicates the code was modified and requires investigation. So essentially, they'll hash the code once they finish writing it, and then you would hash the code yourself once you get it and compare those two. They should be the same because hashing is deterministic, but if they're not, then you know something went wrong. Now, sealing the envelope with code signing. You're going to want to provide cryptographic proof of the author's identity and the code's integrity. The protection confirms code has not been modified by unauthorized individuals and protects against malicious updates. If an attacker tries to deploy a fake patch, the system will reject it because the signature won't match. Now, defending against injection, you can use parameterized queries. So the attack is where clients send SQL code directly to the database server, and input is treated as an executable command. Now, the solution to this is parameterization, which is where the client sends arguments, data, to a precompiled query template. The database treats input strictly as data, never as code. And another bonus benefit of this is that it improves database performance via pre-compilation. Web application firewalls sit directly in front of the web server, intercepting all the traffic, and it operates at layer 7, the application layer, and it scrutinizes input before passing it to the application. Now, why is it needed? Even with input validation, applications contain flaws. WAFs act as a safety net for unpatched vulnerabilities. Now, a case study for this is parameter pollution, where attackers send multiple copies of the same parameter to confuse the web platform. Now, the exploit is the platform might validate the first argument and secure it, but execute the second argument, malicious, allowing the attack to slip through the filters. Most modern systems defend against this, but it persists in legacy unpatched systems or insecure custom code. Now, another containment strategy is sandboxing, which is where you run this code in an environment that is controlled, isolated, and has restricted permissions. The application is limited in its ability to read and write files, interact with the OS, or communicate with other apps. Sandboxes can also be used to deceive attackers, containing them in a benign environment where they believe they are conducting an attack, but they are actually being safely observed. So like Mac, iPhones, iPads, they use sandboxing, so they are pretty invulnerable to attacks. So you're going to want to compare scalability and elasticity when you're thinking about availability. So scalability is the ability to incrementally add computing resources to support increasing demand. But going a step further, elasticity is the ability to automatically provision resources when necessary and automatically deprovision them to reduce capacity and cost when no longer needed. So I think serverless functions are an example of elastic things that automatically provision the resources they need, but they can they are usually more expensive because you're not already stating what you need. So the secure software lifecycle. So in the editor, you're going to want to write clean code, remove comments, manage memory, and handle errors without leaking data. In the supply chain, you're going to want to verify your tools, use code signing, hashing, and trusted repositories. And in runtime, you're going to want to layer your defenses. Use parameterized queries and WAFs. Use sandboxing to contain the inevitable breaches. Because security is not a state, it is a continuous process of validation and defense. Now we're going to talk about secure software and operations. So throughout the life cycle, you're going to want to ensure software security. So the persistence of risk. So 4 of the top 10 breach causes were exploits of overflow vulnerabilities that were 12 to 16 years old. And this is a risk when you use legacy software. Now, when you reuse these third-party libraries, you can also introduce unknown vulnerabilities. So security must address code the organization is not aware it's running. Now, memory leaks are where you would accumulate or provision system memory, but you never give it back. So even if you don't need the memory, you're gonna keep it for yourself, and eventually the system runs out of memory and crashes. To remediate this, you can reboot your system, but you're going to want to fix your code eventually to have garbage collection and such. Now, navigating memory, you're going to want to understand null pointer exceptions. Pointers store the address of another location in memory. Dereferencing is the act of following that pointer to access the data. So if the application tries to dereference a null pointer exception occurs. This can lead to denial of service, a crash, or debugging info leak. So a buffer overflow vulnerability is where an attacker manipulates a program into placing more data into an area of memory than is allocated, and the goal is to overwrite other information with malicious instructions. So analysts must seek a patch for this immediately. Scan reports usually identify the specific patch required. Integer overflow is a variant of buffer overflow, where the result of an arithmetic operation is too large to fit in the specified buffer or container. This can result in the number wrapping around to a negative value or 0, bypassing logic tests. Race conditions occur when security depends on the sequence of events. If there is a gap between checking credentials and using them, then the system can be strict in that window. TOE is the component being tested, that's target of evaluation. TOC is time of check, TOU is time of use, and between those two is a vulnerability window. Unprotected APIs. So services use APIs to allow automation, but if they're not secure, they allow unauthorized function use. So anyone with an API URL could modify the service or access interfaces not intended for the public. So to avoid this, you're going to want to use authentication, such as API keys, and encrypted channels. So vulnerabilities. You're going to want to test your knowledge. So first, in scenario A, a user's access was revoked, but they accessed the file because the system only checked permissions at login. That's a TOC/TOU. Scenario B, an application crashes, and slowly over time it consumes all the RAM until it crashes and you need to reboot. That's a memory leak. And C, an arithmetic operation results in a number too large for its assigned container, and that's an integer overflow. Now, two vectors of web attacks are injection and scripting. So SQL injection is timing-based. Timing-based is an example, but SQL injection overall is attacking the database layer to retrieve or manipulate data. So this wait for delay is an example of a timing-based where if the database pauses, then you know it worked. Then cross-site scripting is where you put a script into a website where it's supposed to execute and it executes. So reflected is where it's in the link and stored is where it's stored on the server. So when you're hijacking the user session, you get a session cookie. You can use the session cookie for session hijacking, which is where an attacker uses a stolen session cookie to impersonate the user. You can do request4j, CSRF, which is tricking a user's browser into executing unwanted actions. And directory traversal, which is where you use these // characters to escape the web root and access system files. So, for example, they could access /etc/password. To fortify the application layer, you're going to want to do input validation, parameterized queries, code signing, and sandboxing. And to shift the automation, you're going to want to do this because it increases efficiency, it enforces baselines, it multiplies your workforce capacity, and it also increases worker retention because they no longer have to do these mundane tasks. So IAC, or infrastructure as code, are scripts that configure systems to ensure uniformity. So core use cases for security automation include access management, so that's user provisioning, automatically adding and removing access, and guardrails, which is where you enforce policy controls. Then there's operation, where ticket creation streamlines routing, and escalation auto alerts key personnel. And then there's resource management, which is where you automatically allocate and provision system resources and enable and disable services based on triggers. Now, for orchestration and scripting tools, we have SOAR, which is security orchestration, automation, and response. This automates tasks across multiple systems. These processes must be repeatable and require no human interaction. Scripting includes Python, Bash, and PowerShell. It's used for log analysis and network scanning. And then we have API integration, the glue that enables data exchange between these tools. Now, what are the risks of automated systems? So there's a single point of failure. So one malfunctioning script can crash operations across the enterprise. There's technical debt, where the scripts become outdated and inefficient as systems evolve. There's complexity and cost, where a high upfront investment requires specialized skill. And there's ongoing supportability, because maintenance is a continual resource drain for automation. Now remember, automation is not set and forget. You need to maintain it. So look at these three scenarios and see, test your knowledge. If you can get this right, and just pause if you need to look at it. Now in an analyst lab, they can decode these server logs and see what's going on and do some log analysis. So exam essentials, in development, you're going to want to follow standardized SDLC and align with OWASP principles. For attack indicators, there are memory injection, buffer flow, overflow, race conditions, SQL injection, and cross-site scripting. Then we have key controls, input validation, parameterized queries, code signing and sandboxing, and automation logic, where the benefits are enforcing baselines, but the risk is single point of failure. And the future of secure operations, where cybersecurity professionals must bridge this gap, ensuring software undergoes rigorous testing on the micro scale while leveraging orchestration to defend at scale, the macro scale. Automation is not a replacement for intelligence, it's a force multiplier. And that is it for these slides. So thank you for sticking along. 105 slides. Hopefully you were able to glean an understanding about application security. Goodbye.